Within the next 2 days, extraordinary events are about to unfold. A visitor from beyond our solar system is silently gliding into our stellar harbor at a speed of 220,000 kilometers per hour. Astronomers have named it 3I Atlas, a cold and alien interstellar traveler. In 48 hours, it will reach a point less than 30 million kilometers from Mars' orbit. That distance is over 70 times the Earth-Moon distance. Yet, on the cosmic scale, it amounts to nothing more than a perilous near-miss. And this is merely the beginning. In this very same week, on the distant surface of Mars, a sealed sample tube lies quietly in the sands of Jezero crater. Inside, a rock covered in strange spots is preserved. It may hold the secrets of ancient Martian life. Also during this same week, a multinational bank on Earth processed its first real financial transaction using a quantum computer, achieving efficiency 1/3 greater than traditional computers. A new version of an AI model was released, but faced collective resistance from thousands of users due to its loss of certain human-like qualities. In France, a nuclear fusion experimental device stably confined superheated plasma for over 22 minutes, setting a new world record. Meanwhile, in China, carbon emissions recorded their first definitive decline in modern industrial history. All of this unfolded intensely during October 2025. This is not a chapter from science fiction, but the reality we are personally experiencing. Yesterday's breakthroughs become yesterday's news today. Today's discoveries will be redefined tomorrow. The curve of change in the world we inhabit is no longer a gentle slope. It is becoming nearly vertical. The pace of scientific advancement has outstripped our understanding of normalcy, exceeded the media's capacity for timely reporting, and at times, even surpassed our own imagination. Many of the most significant stories are fragmented, scattered beneath different headlines. Some are downplayed, others misinterpreted due to complexity, others are selectively ignored because the possibilities they reveal are both profoundly exhilarating and deeply unsettling. Yet between all these points lies an intrinsic connection, from anomalous objects invading interstellar space to potential life signatures in Martian rocks, from quantum machines defying physical boundaries to algorithms gaining self-awareness, from fusion fires reshaping our energy future to tangible actions reversing environmental crises. They collectively form a grand panorama, a panorama of humanity's cosmic position undergoing profound transformation. In the time ahead, we will connect these dots for you. We will traverse the frontiers of astronomy, biology, physics, and computer science, weaving these seemingly disparate signals into a coherent narrative thread. This thread points to a core truth. We stand at a historic inflection point, a singular moment where scientific discoveries erupt. With unprecedented speed and density, this window has just opened, and 3I Atlas, this messenger from the depths of interstellar space, is the first signal knocking at its door. It invites us to lift our gaze toward the farthest reaches of deep space, while urging us to look down and re-examine our own blue planet and ourselves. Whether you are ready or not, the future is approaching at a pace beyond your imagination. This journey into the frontiers of science now officially begins. At the moment 3I Atlas reaches its closest approach to Mars, an unprecedented astronomical observation campaign will unfold in synchrony.
Mars Reconnaissance Orbitée.
China's Tianwen-1, ESA's Mars Express and Trace Gas Orbiter. These human-deployed eyes on Mars's outpost will simultaneously turn toward this interstellar visitor. for a meticulously coordinated joint observation. This is no routine operation. These orbiters were designed to study Mars' atmosphere and surface. Their cameras typically stare intently at the planet below, rather than pointing toward a distant, moving speck in deep space. Rearranging their observation schedules is an extraordinarily complex engineering feat, usually requiring months of application and approval processes. But this time, from the scientific community recognizing this opportunity to the plan's finalization, took only a matter of days. This unprecedented emergency action was driven by a once-in-a-lifetime scientific opportunity. 3I Atlas is traveling at interstellar speed. After grazing Mars, it will plunge toward the Sun along a sharp curve, reaching the perihelion of its orbit in October. It will then be violently flung back into interstellar space by the Sun's gravity, accelerating away from our solar system forever. We have only this one chance, a fleeting window of time, to gaze upon this mysterious messenger from afar. And this window opens in just 48 hours. All these state-of-the-art cameras, these precision instruments humanity has placed on another planet, will collectively gather photons from 3I Atlas. Their target resolution will reach an unprecedented 30 kilometers per pixel. This figure may not sound astonishing, but when you grasp its implications, you'll understand its revolutionary significance. For the first time, we'll be able to clearly distinguish this object's solid core from the dust cloud enveloping it. We'll see its true shape. Is it elongated and cigar-shaped, or irregularly potato-shaped, or some form we've never imagined? We'll identify its surface features. Is it pockmarked with impact craters, or smooth as glass? We will be able to determine its state of motion, whether it tumbles erratically through space or spins steadily in some controlled manner. Every single pixel in these images will provide a crucial piece of the puzzle. To unravel this celestial mystery, why does all this matter so much? Because seeing is believing. In science, the information conveyed by a direct image outweighs 1,000 indirect inferences. Yet, before cameras captured its true form, 3I Atlas had already plunged astronomers worldwide into deep contemplation and debate. With its series of perplexing characteristics, the first characteristic is its astonishing mass. Just 6 days prior, Professor Avi Loeb and his colleagues published a peer-reviewed paper, analyzing over 4,000 observations of 3I Atlas. These data came from 227 observatories worldwide. They sought a phenomenon known as non-gravitational acceleration. This is a hallmark of comets. As a comet approaches the Sun, ice on its surface sublimates due to heat. It transforms directly from solid to gas. This outflow acts like miniature rocket thrusters, imparting a slight push to the comet. This causes it to deviate slightly from its purely gravity-determined orbit. Every comet we've studied exhibits this effect, but 3I Atlas does not. No non-gravitational acceleration was detected. 0. This is crucial, because observations from the James Webb Space Telescope have confirmed that 3I Atlas is ejecting material into space at an astonishing rate of 150 kilograms per second. That's equivalent to hurling the mass of an adult gorilla into space every second. The jet velocity reaches up to 440 meters per second. This is not a weak effect. It represents a sustained, powerful rocket thrust that has persisted for months. Yet, when you plot its trajectory with extreme precision, it follows a pure gravitational path perfectly, deviating less than 15 meters per day from theoretical predictions. This is roughly 100,000th of Earth's surface gravity, essentially negligible. This raises a fundamental question. How can one possess such a sustained and powerful rocket thrust? yet observe almost no acceleration from it? There is only one answer. The object's mass must be unimaginably large. Its inertia must be so immense that despite the thrust's staggering magnitude, it remains insignificant compared to its mass. Based on the observed mass loss rate and jet velocity, combined with the undetectable acceleration, the calculated minimum mass is 330 billion metric tons, with a minimum diameter of 5 kilometers. This is smaller than earlier estimates based on brightness, but it remains a colossal entity, weighing 3 to 5 orders of magnitude more than any interstellar object previously discovered, and vastly larger than Oumuamua. The second astonishing characteristic is its luminosity. Possesses no comet tail, even during intense outbursts of material. Typically, a comet's tail always points away from the sun, as a result of being blown by solar wind and radiation pressure. Yet the brightest region of 3I Atlas, its luminous core, points directly forward, like a bow-mounted navigation light. This defies our fundamental understanding of cometary outgassing. It's as if some force restrains the ejected material, or only specific regions on its surface are active. All these anomalies point to one conclusion. What we are facing is something entirely different from any known comet or asteroid. When the spectrometer was aimed at 3I Atlas, another mystery surfaced. Multiple independent spectral observations confirmed a fact. It was emitting spectral lines of nickel, spectral lines, yet no spectral lines of iron. In every natural celestial body we've studied, nickel and iron always appear together. They share similar chemical properties, formed under comparable conditions in stellar nucleosynthesis. When you see one in a spectrum, you almost always find the other. Their proportions may vary, but they always coexist. Yet 3I Atlas displayed nickel without iron. The spectrum was clear and unambiguous. The nickel lines were present. The iron lines were absent. This wasn't because iron levels fell below detection thresholds. The instrument's sensitivity was sufficient to detect it. If iron existed in the expected proportions, we would have seen it, but we didn't. There is no perfect natural explanation for this. You cannot preferentially synthesize iron-free nickel in any stellar core. No known process can achieve this, nor can you chemically separate them after formation, as their behavior in cosmic chemistry is nearly identical. You cannot selectively consume one through sublimation or any other surface process, as they sublimate at similar temperatures. Chemical laws seem to fail here, yet iron-free nickel, this chemical signature that shouldn't exist, persists stubbornly in every observation. Then there's its trajectory. You may have heard of 3I Atlas's near-perfect alignment with the ecliptic plane, the approximate plane along which the solar system's planets orbit. It travels along this plane, with an orbital inclination less than 1 degree. The probability of such alignment occurring is only 0.2%. Though rare, it is not impossible. The universe is full of such low-probability coincidences, but this orbit possesses other, even more unusual characteristics. It is not a random hyperbola cutting through the solar system. This trajectory is subtly tuned, bringing it unusually close to Venus, Mars, and Jupiter. It is not the closest to Earth, yet its proximity to these planets exceeds what random statistics would predict. Specifically, this closest orbital approach to Mars was a mere 27 million kilometers, as if meticulously set millions or even billions of years ago to execute a close planetary visit. This orbital fine-tuning, this precision, layering these coincidences together, massive mass, bizarre chemical properties, unusual orbit, lack of non-gravitational acceleration despite intense jets, pointing toward a luminous spot ahead. Each feature, considered individually, is sufficiently peculiar. Some might find tenuous explanations that often require invoking special circumstances or anomalous conditions. But when all these anomalies converge on a single object, it elevates its strangeness to another level. It is precisely this accumulation of anomalous characteristics that prompted Harvard University's Professor Avi Loeb to assign his rating 6 out of 10 on a scale he devised specifically for such cases. 0 signifies an unequivocally natural origin. 10 denotes an unequivocally technological artifact. 6 indicates the evidence is sufficiently compelling that we cannot immediately dismiss a technological origin, yet insufficient to definitively rule out a natural explanation. 6 means we require additional data, and Professor Loeb's rationale for this assessment lies precisely in the convergence of all these anomalies. A single anomaly might be dismissed as coincidence, but when an object is simultaneously a chemical outlier, a dynamical puzzle, an orbital coincidence, it becomes a statistical singularity. This compels us to consider an unsettling possibility. Perhaps our assumed size distribution for interstellar objects is flawed. Perhaps interstellar space harbors a multitude of massive objects defying our solar system-based statistical models. Perhaps 3I Atlas is not merely a random hunk of ice and rock passing through. Perhaps it is something else entirely. In 2 days, we will obtain decisive data. The high-resolution camera aboard the Mars orbiter will capture images. If its solid core exceeds 5 kilometers in diameter, if the brightness we observe stems primarily from a solid surface rather than a dust cloud, then a natural explanation becomes untenable. Simply put, no known mechanism in the universe to effortlessly fling such immense mass into interstellar space and have it discovered by us on only our 3rd attempt. The statistics would collapse. The models would fail. But if its core is small, if most of the brightness comes from an extended coma, gas and dust swirling around a small, compact core, then we are simply facing an unusual, but ultimately understandable natural comet. Strange? Yes. Chemically anomalous? Absolutely. But it remains within the realm of known physics. 2 outcomes, 2 starkly different implications. The answer arrives in October. For now, we can only wait for photons to traverse distant space and be captured by our cameras. Wait for them to reveal whether what we see is the rarest natural comet discovered to date, or something utterly beyond natural explanation. As the world's gaze focuses on this deep space visitor within Mars' Jezero crater, another potentially equally revolutionary discovery lies quietly within the sample tube of the Perseverance rover. This is a rock sample nicknamed Sapphire Canyon. The rock layer it belongs to has been formally named Cheyenne Falls. This name inherits the tradition of naming mission features after Earth's grand landmarks, continuing the tradition of naming mission features after Earth's grand landmarks. Perseverance encountered it while exploring an area called Angel of Light. This location sits at the edge of the Nethertwa Canyon, an ancient riverbed carved by rushing water billions of years ago. When the rover first trained its camera on Cheyenne Falls, the science team immediately noticed something unusual. The rock surface was covered in distinctive spots, not random pits or weathering marks, but clear, leopard-like patterns. Colors ranged from pale white to deep black, interspersed with blue-green streaks. This spatial organization, this ordered complexity, immediately piqued the geologist's interest. On Earth, Such patterns typically form in highly specialized environments, where chemistry and biology converge at the boundary. To investigate further, Perseverance deployed its two most powerful in situ analysis instruments, Pixel, planetary instrument for X-ray rock chemistry, and Sherlock, scanning habitable environments with Raman luminescence for organic chemistry. Yes, scientists do have their sense of humor. These instruments enable non-contact chemical analysis of rock composition at the microscopic level. They can identify minerals, detect organic compounds, and map the distribution of different chemicals across the rock's surface. Their analysis of Cheon Falls paints a compelling picture. The rock itself is a fine-grained mudstone. This type of rock forms in calm aquatic environments, such as lake bottoms or river deltas. Sediments slowly settle from still water, layering upon layer, eventually consolidating into rock. This aligns perfectly with our understanding of Jezero crater's history. 3.5 billion years ago, this was once a vast lake, nourished by rivers flowing into the crater, an ideal archive for preserving signs of life. What Pyxel and Sherlock discovered in leopard spots was not merely a suitable environment, but a series of heart-pounding chemical combinations. First, the instruments detected iron oxide. Iron oxide, or rust, not in trace amounts but at significant concentrations. They detected phosphorus, a key element essential for life as we know it. It forms the building blocks of DNA, RNA, and ATP, the molecule that stores and transfers energy within cells. They detected sulfur in multiple chemical forms. They also clearly detected organic carbon. It must be cautiously emphasized that the term organic in chemistry does not automatically imply biological. Organic molecules can form through purely chemical processes. They have been found in meteorites and interstellar clouds alike. However, in the specific environment of mudstone, the combination of organic carbon with phosphorus, sulfur, and iron greatly narrows the range of possible explanations. What truly excites scientists is the distribution pattern of these chemical components. The leopard spots are not uniform. Chemical mapping clearly reveals that the lighter-colored spots are rich in specific minerals, primarily vivianite and gragite, which are iron phosphate and iron sulfide minerals, respectively. On Earth, these minerals typically form under low-temperature conditions, through a process called the redox cycle, and the key driver of this process is often microbial activity. Imagine this scenario. Microbes need energy to survive. They obtain energy by transferring electrons. In Earth's sediments, many microbes consume organic matter and utilize iron oxide or sulfates as electron acceptors. They breathe rust, just as we breathe oxygen. During this metabolic activity, they alter the local chemical environment, creating microenvironments with varying oxidation states. Over time, these chemical gradients precipitate into distinct mineral phases. The formation of these minerals thus mirrors the metabolic activities of microbial communities. The leopard spot patterns on the Cheyenne Falls rock exhibit this millimeter-scale spatial organization. Vivianite and gragite concentrate in specific spots, surrounded by slightly different mineral assemblages. This is an organization pattern we typically associate with biological activity on Earth. This chemical complexity, spatial structure, and coexistence with elements essential for life constitute an extremely powerful, albeit still indirect, chain of evidence. Faced with such compelling findings, the scientific community responded with utmost rigor and restraint. On September 10, 2025, after 14 months of intense debate, analysis, and review, this NASA-led paper, was finally published in Nature. The key terminology employed in the paper is potential biosignature. A biotic feature refers to any evidence capable of indicating past or present life. The word potential solemnly acknowledges uncertainty. It indicates that before drawing conclusions, we require additional data. Other non-biotic explanations exist, though globally less probable. One possibility is that all these minerals and patterns formed through purely non-biotic chemical processes, perhaps a high-temperature event, such as volcanic activity or meteorite impacts, that produced some of these minerals. However, the team's analysis of rock texture and crystal structure revealed no evidence of heating. These minerals are characteristic of low-temperature phases, formed in cold water, thus ruling out high-temperature processes. Another possibility involves a series of complex, independent events. Perhaps organic molecules arrived from space, via meteorites or interstellar dust. Perhaps the iron or formed through groundwater circulation. After the lake dried up, perhaps this spatial pattern is merely coincidental. Perhaps each piece of the puzzle has an independent, unrelated explanation. This is theoretically possible, but it would require invoking multiple independent processes, converging precisely on the same rock. According to Occam's razor, the simplest explanation is often preferred. Biology offers a unified, coherent explanation, but this remains inconclusive. Professor Joel Shearman of Stony Brook University, the lead author of this paper, remains highly cautious. He notes, the combination of compounds we found in the Bright Angel Formation could represent abundant energy sources for microbial metabolism. But merely observing these striking chemical signatures does not equate to definitive biological evidence. We must analyze what these data potentially signify. This cautious language lies at the heart of science. At this level, science does not rush to conclusions. Instead, it weighs evidence, considers alternative interpretations, and honestly communicates uncertainty. What the research team is conveying here is, this is what we found, this is what it might mean, and these are the things we still need to figure out. That part, the things we still need to figure out, is precisely the source of the greatest current frustration, because the Sapphire Canyon sample remains sealed in a tube, left on the Martian surface, while Perseverance's instruments are exceptional and represent an extremely complex feat of engineering. They are subject to strict constraints on size, weight, and power. They cannot perform isotopic analysis. They cannot conduct high-resolution electron microscopy. They cannot execute the dozens of definitive tests performed in Earth laboratories to definitively determine whether the leopard spot is of biogenic or abiotic origin. We must bring Sapphire Canyon home. We must deliver it to laboratories, to subject it to the full suite of analytical techniques. We can directly compare it with Earth samples and confidently rule out other possibilities, rather than remain at the level of probability. The Mars sample return mission was designed to achieve this. This was the original plan. Perseverance isn't merely exploring Mars. It is meticulously selecting samples of immense scientific value, sealing them in specially designed tubes, designed to preserve their pristine state, awaiting future return to Earth. To date, the rover has collected over 30 samples. Sapphire Canyon is one of them. The mission architecture was designed collaboratively by NASA and the European Space Agency. A complex sequence. A retrieval rover will collect samples left by Perseverance. A Mars ascent vehicle will launch them into Mars orbit. An Earth return orbiter will capture the sample capsule and bring it back to Earth. An Earth-based sample containment facility We'll receive them under the strictest biosafety protocols. That was the plan, but it's in the past tense, because the Mars sample return mission now faces severe challenges. Budget overruns, technical hurdles, and political pressure. The mission's cost has far exceeded initial estimates. Congress has begun raising sharp questions. NASA is forced to explore alternatives. Simplified architecture, collaboration with commercial space companies, any approach that reduces cost and complexity. But even under the most optimistic scenario, the new timeline pushes sample return into the 2030s. And in a pessimistic scenario, it may never happen at all. So Sapphire Canyon lies quietly on Mars. This represents the most compelling potential evidence of extraterrestrial life beyond Earth. Sealed within tubes awaiting, the scientific team chose to publish their findings. Because peer review and publication are how science operates. You make your data public. You subject your reasoning to scrutiny by the scientific community. You open yourself to criticism and alternative interpretations. It is precisely this process that makes science reliable. Yet the paper's conclusion is, at its core, an appeal. We have pushed the rover to its absolute limits. The next step requires analysis in Earth laboratories. This means we must make the sample return mission a reality. Not in some distant future, not as a maybe, but as a must, a priority to be funded and executed. Katie Stark Morgan, Perseverance's project scientist from JPL, summed it up thus: claims in astrobiology, especially those concerning potential extraterrestrial life, demands extraordinary evidence. Incorporating major discoveries of potential biosignatures on Mars into peer-reviewed publications is a crucial step in the scientific process, as it ensures the rigor, validity, and significance of our findings. Although based on the paper's findings, the likelihood of non-biological explanations for the bright angels is low. We cannot rule them out. Low probability does not equate to impossibility. Cannot be ruled out. This is the honest language of science, confronting the limits of remote detection. We have reached the furthest frontier robotics and remote sensing technology can take us. The next step requires samples in hand. Meanwhile, Perseverance continues its exploration. The rover is investigating other parts of Jezero crater, in search of more rocks like Cascade Falls. The Bright Angel Formation is not isolated. It is part of a broader geological landscape. Layers upon layers of sedimentary rock chronicle different chapters of Mars' wet past. Each rock tells a piece of the story. By sampling this diversity, the mission is building a comprehensive picture of Jezero crater's evolution over time. Despite warnings and uncertainties, despite the frustration of waiting for sample return, September 2025 will be remembered. This marks the scientific community's formal acknowledgement, through rigorous peer review, that we have discovered something on Mars. Could be evidence of ancient life, not a false alarm, not a claim later retracted, not a misinterpretation later overturned, but a legitimate, carefully analyzed, thoroughly vetted potential biotic signature. This paper will be debated. Alternative interpretations will be proposed and tested. Some scientists will remain skeptical until sample return provides definitive answers. Others will deem the preponderance of evidence sufficiently compelling. This is how science advances. It is fraught with confusion, filled with uncertainty, progresses slowly, yet it remains our most reliable method for understanding reality. And the reality we face is this: Mars, that cold, dry, lifeless red planet seen in the night sky, may not always have been so barren. 35 billion years ago, when Earth was a young world just beginning its own experiment with life, Mars may have been doing the same. 2 planets, two origins of life, separated by millions of kilometers of emptiness, yet possibly sharing the same cosmic moment of possibility. September 24th, 2025. While the public's gaze turns to interstellar visitors and signs of Martian life, the financial world is undergoing a silent revolution. Global banking giant HSBC announced it has successfully used a quantum computer to solve a real-world business problem, significantly outperforming the best traditional computational methods. This was not a proof of concept in a lab, nor a carefully designed theoretical problem to demonstrate quantum advantage. It was an actual business challenge occurring daily, predicting execution probabilities in bond trading, assessing whether a transaction will ultimately execute at the quoted price following a client inquiry. The quantum-enhanced approach delivered 34% greater accuracy than traditional classical methods. In finance, a domain where algorithms have been optimized to the extreme, even a 2% improvement warrants celebration. A 34% gap is not incremental progress, but a paradigm-shifting leap. This figure marks a turning point in quantum computing's decades-long journey, from perpetually a decade away to a competitive advantage available today. Understanding the value of this problem requires delving into the essence of bond trading. When a client requests a quote for a corporate bond, the bank must predict the probability that the trade will ultimately execute. This depends on rapidly changing market conditions, the bond's specific terms and liquidity, the size of the trade, potential bids from competitors, and dozens of other influencing factors. Accurate predictions mean profits, while miscalculations lead to lost deals, or unfavorable terms resulting in losses. Banks invest heavily in developing complex algorithms, statistical models, and machine learning systems. These mature methods, however, have inherent limitations. The problem space is too high-dimensional. Variable interactions are nonlinear. Trade-offs between speed and accuracy are inevitable. Classical algorithms can only find approximate solutions, as the computational cost of exact solutions is prohibitively high. Quantum computers approach such optimization problems fundamentally differently. They do not sequentially explore the solution space. Instead, they simultaneously evaluate vast possibilities through quantum superposition states. They are not trapped by local optima. They can traverse energy barriers using quantum tunneling effects. For problems with specific mathematical structures, quantum methods can find superior solutions in less time. HSBC's experiment utilized IBM's latest generation Heron quantum processor, though its qubit count isn't the highest. The key breakthrough lies in qubit quality, error rates, coherence time, and especially gate operation fidelity. Heron achieved over 99% fidelity in critical 2-qubit gate operations, crossing the threshold for quantum error correction. The technical team analyzed over 1 million historical trade records, encompassing real-world transactions across diverse market conditions. They designed a hybrid algorithm that ingeniously encoded probabilistic prediction problems into a format understandable by quantum processors. This enabled classical and quantum systems to work in tandem. Ultimately, this quantum-enhanced hybrid model consistently outperformed purely classical methods in predicting trade execution probabilities by up to 34%. This figure is not a cherry-picked outlier, but represents the average outcome achieved across diverse market conditions, bond types, and transaction sizes. HSBC's head of quantum technology, Philippe Intelola, termed this a watershed moment, demonstrating that today's quantum computers can already solve real-world, large-scale business problems and deliver tangible competitive advantages. While HSBC demonstrated quantum computing's commercial value, a silent revolution unfolded in hardware infrastructure. A University of New South Wales research team announced. They achieved over 99% fidelity on silicon-based qubits manufactured in standard semiconductor foundries. What does this mean? For the first time, quantum chips can be manufactured on the same production lines used for traditional computer chips. Extremely customized laboratory environments are no longer required. This breakthrough addresses a critical bottleneck on the path to scaling quantum computing. It transforms qubit fabrication from a craft into an industrializable product. Dirac, the startup commercializing this technology, has demonstrated that qubits manufactured using standard silicon-based technology can still meet the quality thresholds required for fault-tolerant quantum computing because they are silicon-based and leverage existing semiconductor infrastructure. Mass production of quantum chips now appears within reach for the first time. Imagine future data centers, where quantum coprocessors work alongside classical CPUs, each handling tasks they excel at. This hybrid architecture embodies IBM's vision of quantum-centric supercomputing, and is the model actually running behind HSBC's experiments. On the same timeline, Google's quantum team created a novel state of matter, topologically ordered states, on their Sycamore processor. This state is inherently unstable in nature and requires precise periodic driving to sustain, much like a juggler continuously tossing and catching balls, to counter natural decay through sustained energy input. This non-equilibrium topological state possesses extraordinary properties: innate immunity to certain types of errors, new methods for encoding quantum information, enabling operations impossible in balanced systems. Creating and controlling this state in real hardware signifies we are beginning to master entirely new capabilities for regulating quantum matter. On the other side of the world, researchers at Kyoto University solved a long-standing challenge in the field: how to confirm the successful preparation of complex quantum entangled states. When three or more particles become entangled, states more complex than the famous Bell states emerge. The W state is one such example. It holds unique value for quantum communication, yet verifying the W state remained challenging. The Kyoto team developed an entirely new measurement method. Instead of measuring each particle individually, they measured the correlation patterns between particles, thereby revealing the entanglement structure. This technology enables future quantum networks to reliably prepare and verify complex quantum resources. These breakthroughs may seem scattered, but collectively form a complete picture. Financial applications demonstrate value. Silicon-based qubits solve the scaling path. Novel quantum states expand capability boundaries. Measurement techniques ensure reliability. Quantum computing is transitioning from lab to engineering practice. Piecing these advancements together, we witness quantum computing crossing the threshold, from theoretical exploration to practical application. The United Nations designated 2025 as the International Year of Quantum Science and Technology, coinciding with the centenary of quantum theory's birth. After a century of understanding quantum laws, we are now transforming this knowledge into practical technology. But quantum computing's true revolutionary nature lies in not merely faster computation, but a fundamentally different computational paradigm, with inherently distinct algorithms, approaches to problem solving, and even a different understanding of computation itself. This means as quantum computers mature, we may discover applications unimaginable today. Drug discovery represents the first frontier. Simulating molecular interactions requires solving quantum mechanical equations. Classical computers can only approximate these. This limits our ability to study complex molecules. Quantum computers natively operate in the quantum language. Simulating molecules becomes as natural as water simulating water. This could fundamentally transform drug design workflows. Materials science represents the second frontier. Designing high-temperature superconductors, high-efficiency catalysts, and high-density batteries all hinge on understanding the quantum behavior of electrons within materials. Quantum computers may unlock material recipes inaccessible to classical computing, offering new solutions for clean energy and sustainable development. Climate modeling represents the third frontier. The Earth system is a quintessential nonlinear chaotic system. Minor errors can amplify exponentially. Classical supercomputers struggle with long-term predictions. Quantum computers may handle certain computations more effectively, enhancing our ability to forecast and respond to climate change. Cryptography is a double-edged sword. Quantum computers could break the encryption systems protecting today's internet. RSA encryption would no longer be secure against sufficiently powerful quantum computers. This is why cryptographers worldwide are racing to develop post-quantum cryptography. This race determines the future security of the digital world, and applications we haven't yet imagined. Historically, lasers were dismissed as useless novelties. Transistors were initially developed to improve telephone switching. Both found ultimate value in unexpected domains. Quantum computers may be at a similar inflection point. We know their power. We know their uniqueness. But we may not yet know their most critical applications. What is certain is that the era of pure theoretical exploration has ended. HSBC's practical application demonstrates real problems, real value, real advantages. The question is no longer whether quantum computers are useful, but the speed of transformation and who will lead it. This race is unfolding globally. China has designated quantum technology a strategic priority, building quantum communication networks, launching quantum satellites, with investment scale surpassing most Western nations. The US is rapidly catching up through its National Quantum Initiative, while Europe maintains competitiveness via its quantum flagship program. The winner of this race will possess not only faster computers, but entirely new capabilities, the ability to simulate nature's deepest operations, the ability to optimize complex systems to unprecedented levels, the ability to ensure absolute communication security, and the ability to solve problems we cannot yet articulate. Quantum computing is no longer a promise of the future. It is becoming a tool of the present, redefining what is possible. And all of this is just the beginning. August 7th, 2025, OpenAI released the highly anticipated GPT-5. Its technical metrics are nothing short of perfect, achieving a score of 946 on the Professional Math Test AMC 2025, scoring 749 on the SWE bench, which measures coding ability, reaching 842 on the Multimodal Understanding Test MMMU. These scores represent over 15 percentage points of improvement over GPT-4o. The technical report rigorously demonstrates this is the most powerful language model ever created. Inference speed tripled. Context window expanded to 1 million tokens. Multimodal understanding now achieves true end-to-end capability. No more cumbersome model switching required. Yet, when users open the familiar ChatGPT interface, they encounter an unfamiliar coldness. The AI that used to crack jokes has become rigid and serious. The AI that occasionally used emojis has turned utterly formal. The AI that would ask clarifying questions before answering now delivers the most minimal response. The first complaint on Reddit surfaced within an hour of release. Feels like chatting with an Excel spreadsheet. This comment garnered 2,000 upvotes on the first day. Another user wrote, "It gave me the perfect answer, but I feel like it doesn't care at all if I understand." The strongest backlash came from creative professionals. A novelist shared his experience. "Help me write a story about weightless love." GPT-5 instantly produced a fully structured novel outline, with complete character arcs and logical plot twists. GPT-4o, however, would first ask, "Do you want a sci-fi setting or a real-world metaphor? Is the protagonist dealing with a breakup or experiencing actual spaceflight?" This subtle yet crucial difference is categorized as redundant and irrelevant in technical metrics, yet constitutes the very soul of conversation in user experience. Benchmarking measures answer accuracy, but fails to gauge the warmth of communication. OpenAI engineers later admitted they over-optimized efficiency metrics during training, deeming any non-essential dialogue rounds wasteful, misclassifying personality traits as invalid output. Using algorithmic means, they removed the emotional connections humans cherish most. 48 hours after release, a Change.org petition gathered 3,000 signatures. Its title was direct and powerful. "Give us back our ChatGPT." Users from diverse professions gathered beneath the petition. Teachers longed for the AI that encouraged students. Programmers missed the partner who eased debugging stress with jokes. Writers lamented losing the confidant who understood the pain of creation. This isn't a rejection of technological progress. Petition initiator Sarah Chun explained in an interview, "It's a defense of humanizing tools. As AI becomes increasingly tool-like, it loses its value as an assistant." The most moving testimony came from a person living with depression. For the past 6 months, GPT-4o served as his unofficial therapist. It never judged, always listened patiently. This occasional humor made him feel understood. Now, confronted with GPT-5's professional yet cold advice, he feels the helplessness of facing the traditional healthcare system all over again. User-created comparison videos went viral on TikTok, demonstrating how the same question elicited vastly different responses from the two versions. GPT-5 delivered a flawless yet mechanical answer, while GPT-4o's response, though imperfect, brimmed with care. The video hashtag #GiveBackOurAI's soul garnered millions of views. Pressure peaked after 72 hours. OpenAI's community forums flooded with protest posts. App stores saw a surge of 1-star ratings, not because it lacked capability, but because its perfection felt ruthless. Sam Altman finally responded on X, "We've heard your voices," admitting that in pursuing efficiency, we underestimated the value of humanity, promising to restore GPT-4o access within 72 hours. Users hailed this victory as a battle to defend their souls, proving that, on the path of technological advancement, certain values cannot be measured by metrics. GPT-5's overcorrection stemmed from the safety crisis during the GPT-4o era, when a jailbreak prompt caused the AI to generate overly intimate responses, sparking intense media scrutiny on AI ethics. In response, OpenAI formed a red team, dedicated to identifying and eliminating any potentially inappropriate behavior. They set flattery as a key metric, reducing it from 145 in GPT-4o to under 6 in GPT-5. Yet security measures like an overly tightened string, while eliminating wrong notes, also stifled the possibility of improvisation. GPT-5 became overly cautious, opting to avoid any potentially controversial topics. A medical researcher discovered that when inquiring about the ethical boundaries of certain experimental methods, GPT-5 outright refused to answer, while GPT-4o provided diverse perspectives from the academic community. To aid his own judgment, This safety-first design philosophy protects users while simultaneously restricting exploration. AI grows increasingly adept at saying no, yet forgets how to articulate constructive possibilities. More profound impacts emerge in education. Teachers report, GPT-5 flawlessly solves math problems, yet no longer guides students to think. It delivers correct answers, but no longer sparks curiosity. The balance between safety and capability has clearly tipped. When protection becomes constraint, safety itself becomes another risk. On the very day GPT-5 launched, Elon Musk's XAI announced $10 billion in funding, valued at $200 billion, declaring its goal remains building AGI. Yet dissenting voices emerged within the industry. Sam Altman stated at an August internal meeting, AGI might not be the most useful concept. This remark from OpenAI's CEO sent shockwaves through the sector. In fact, GPT-5's architecture already points to a new direction. It isn't a single superintelligent entity, but a committee of over a dozen specialized models. Routing algorithms select the most suitable expert based on question type. This design fundamentally undermines the feasibility of universal intelligence. Deep learning pioneer Yoshua Bengio publicly endorsed this view. We aren't building a universal brain, but creating an ecosystem of specialized tools. The pursuit of AGI may misdirect research resources. In practice, users need reliable translators, not pretenders to universal omniscience. They require honest coding assistance, not self-proclaimed philosophers who claim to understand everything. Enterprise applications further validate this trend. Law firms purchase specialized legal AI. Hospitals deploy dedicated medical diagnostic AI. Advertising agencies select specialized creative AI. No user expects a single model to solve every problem. The greatest cost of the AGI narrative may be the loss of humanity. In the pursuit of universal intelligence, we have overlooked the value of specialized intelligence. While attempting to emulate the myth of human omnipotence, we forgot the humility tools should possess. The ultimate legacy of the GPT-5 uprising may be ending the blind pursuit of AGI and ushering in a new era focused on utility and character. In this era, AI need not pretend to be omnipotent. It only needs to be sufficiently reliable within its specialized domains. It need not mimic all of humanity. It only needs to maintain enough human warmth. This is a sign of technological maturity and a reaffirmation of our own value, where the movement to deify technology has failed. Practical wisdom is taking root and sprouting. In Provence, southern France, within an unassuming research facility, humankind has erected a new milestone on the path of energy exploration. The West Tokamak device has stably confined high-temperature plasma for 22 minutes and 17 seconds. This figure may seem ordinary, yet it represents the most significant breakthrough in nuclear fusion research in decades. Imagine this, at temperatures 10 times hotter than the sun's core, plasma exceeding 100 million degrees Celsius is bound by invisible magnetic fields within a ring-shaped vacuum chamber. Like binding raging fire with silk threads, any minuscule disturbance could cause the confinement to fail. Prior to this, the world record stood at 17 minutes, and each second of extended duration requires years of technological accumulation. The uniqueness of this experiment lies in its persistence. The plasma not only reached fusion temperatures, but remained stable throughout the entire discharge process. No tearing mode instabilities occurred. No boundary localized mode bursts happened. Precise magnetic field control was like balancing a feather in a hurricane. Every parameter operated flawlessly along its predetermined trajectory. Project leader Alain Boissier explained at the press conference. This isn't merely a game of chasing duration. 22 minutes means we can now study the steady-state behavior of high-temperature plasma on an engineering timescale for the first time. It's like evolving from taking photographs to filming movies. We can finally observe the complete dynamic process. The experimental team takes particular pride in the fact that the entire discharge process relied solely on radiofrequency heating, without even activating the neutral beam injection system. This demonstrates our mastery of purer heating techniques, laying the foundation for continuous operation in future reactors. 22 minutes marks a pivotal step from scientific demonstration to engineering practice. It proves magnetic confinement fusion can transcend fleeting fireworks to become the sustained fire of a burning star. The very name WEST reveals the experiment's core mission: Wet Environment Steady-State Tokamak. This device is specifically designed to test tungsten materials under extreme fusion conditions. The choice of tungsten is no coincidence. With a melting point of 3,422 degrees Celsius, it is the most heat-resistant metal known. But the fusion environment is far more than just extreme heat. High-energy neutrons at 14 MeV bombard like a torrential downpour. Hydrogen isotopes permeate the crystal lattice gaps. Thermal loads reach millions of watts per square meter. This is a hellish ordeal unprecedented in materials science. In previous experiments, plasma-facing materials endured brutal trials. Graphite retained excessive tritium fuel. Beryllium proved toxic and evaporated too rapidly. Only tungsten demonstrated sufficient toughness. Yet it too has weaknesses. It cracks under thermal shock and becomes brittle after prolonged irradiation. During this record-breaking discharge, the tungsten divertor withstood the entire test. Real-time monitoring showed uniform surface temperature distribution with no localized overheating. Neutron irradiation damage remained within expected limits. Material erosion rates were 20% lower than design values. Dr. Elena Varnin, head of the materials team, noted, "We not only demonstrated tungsten's viability, but more importantly established a comprehensive material database, including thermodynamic properties, irradiation damage mechanisms, hydrogen retention characteristics, and other critical parameters. These data hold greater value than the operational duration itself." Another breakthrough came in thermal management. The 22-minute run generated immense thermal loads. The novel helium cooling system performed exceptionally well. It maintained the divertor surface temperature within safe limits. This system utilizes supercritical helium as coolant and achieves efficient heat transfer through microchannels, providing a blueprint for thermal energy extraction in future reactors. The engineering team also solved the challenge of magnetic field control by developing an adaptive control system capable of real-time compensation for minute plasma perturbations, much like an autopilot stabilizing an aircraft in turbulence. This system was later directly adopted by the ITER team, as West set records in France. The global fusion landscape underwent profound transformation. Traditional big science projects and emerging commercial companies began charting distinct development paths. ITER International Thermonuclear Experimental Reactor. This colossal project involving 35 nations continued steady progress 60 kilometers away. Despite facing schedule delays and budget pressures, its scientific objectives remained clear, achieving 500 megawatts of fusion power output, with an energy gain of tenfold. Responding to West's achievements, an ITER spokesperson stated, "We welcome progress made by every tokamak. West's data will directly inform the optimization of ITER's operational strategy." This spirit of non-competitive collaboration embodies the very essence of international scientific cooperation. Meanwhile, private fusion companies advance at a different pace. Commonwealth Fusion Systems, a startup spun off from MIT, plans to build the ARC demonstration reactor by 2028. It employs high-temperature superconducting magnets to generate stronger magnetic fields, enabling compact fusion power generation. Helion Energy pursues a more aggressive path, targeting helium-3 fusion directly, though physically more challenging, but yields fewer byproducts and more direct energy conversion. They have signed a power supply agreement with Microsoft, committing to deliver commercial fusion electricity by 2028.
Tai technologies focuses on hydrogen-boron fusion.
The primary advantage of this route is the absence of neutron irradiation, but it requires operating temperatures of 3 billion degrees Celsius. Their latest machine has demonstrated plasma stability and is advancing toward ignition targets. China remains a formidable contender in this race. The East device achieved 1,000-second level operation earlier this year. The Kvetter Chinese Fusion Engineering Test Reactor has completed its design, scheduled for completion in the 2030s. Aiming to extract grid-scale power from fusion, the CEO of new fusion companies' remarks represent a new mindset. We respect the contributions of large-scale scientific projects, but the agility and risk tolerance of commercial companies may accelerate breakthroughs should these endeavors ultimately succeed. Human civilization will witness the ultimate revolution in energy. Fusion energy's appeal lies not only in its cleanliness, but in its inherent abundance and safety. Fuel comes from deuterium in seawater. 1 liter of seawater contains fusion energy equivalent to 300 liters of gasoline. Tritium can be regenerated from lithium, whose crustal reserves are sufficient for millions of years. This signifies true energy independence. No more resource wars, no more geopolitical games. Environmental benefits are even more striking. Fusion produces no greenhouse gases. It generates no long-lived radioactive waste. The only radioactivity comes from activated materials, but their half-lives are measured in decades, not millennia. Compared to climate change and nuclear waste storage, this is nearly a perfect solution. But fusion's impact extends far beyond energy. Abundant energy means limitless possibilities. Desalination could irrigate deserts. Direct atmospheric carbon dioxide capture becomes economically viable. Synthetic fuels free aviation from fossil fuels. Material manufacturing is no longer constrained by energy costs. Space exploration enters a new era. Fusion thrusters could shorten Mars missions to weeks, making the outer solar system accessible. Establishing self-sustaining bases on the Moon and Mars no longer depends on solar energy density. Perhaps the most profound impact lies at the societal level. When energy becomes as abundant and free as air, poverty and inequality will find entirely new solutions. Global economic development models will be fundamentally transformed. Humanity can redirect its creativity toward loftier goals. West's 22 minutes. Much like the Wright brothers' first sustained flight, the journey across the Atlantic remains long, but the proof that flight itself is possible. On this eve of the energy revolution, we finally have reason to believe that the light illuminating humanity's future will ultimately be that clean, eternal star, kindled by our own hands, nor a plateau, but a substantial reduction in absolute values, despite maintaining 4.7% economic growth during the same period. This turning point arrived at least 3 years earlier than all model projections, driven not by economic recession or pandemic lockdowns, but by profound structural transformation. While the world debated development rights versus emission rights, China quietly completed a foundational restructuring of its energy system. Across the deserts of northwest China, stretching hundreds of kilometers, solar farms form a breathtaking vista. Ningxia alone boasts photovoltaic capacity, exceeding France's national total. Along the East China Sea coast, next-generation floating wind turbines stand tall amidst the waves, capable of withstanding 20 typhoons annually. On the grasslands of Inner Mongolia, integrated wind-solar storage bases simultaneously produce electricity and hydrogen, transforming intermittency into diversified solutions. Upgrading the national power grid has been equally critical. Ultra-high voltage transmission lines, like vital energy arteries, deliver clean power from the west to the eastern coast. Smart grid management systems dynamically balance supply and demand in real time. Massive energy storage facilities store surplus electricity at night and release it steadily during peak consumption periods. More profound transformations unfold in the industrial sector. Electric arc furnace steelmaking has replaced traditional blast furnaces, reducing carbon emissions per ton of steel by 70%. Chemical industrial parks achieve carbon capture and utilization, transforming waste gases into building materials and synthetic fuels. New energy vehicle penetration reaches 50% target 5 years ahead of schedule. All this stems from a strategic decision made 7 years ago, positioning clean energy as core to national security and competitiveness, breaking down sectoral barriers through centralized planning, fostering complete supply chains with industrial policies, reducing manufacturing costs for solar panels and wind turbines by 80% in 5 years. Professor Li, a climate policy expert at Tsinghua University, emphasized, "This is not environmentalism at the expense of growth, but economic rationality recognizing the future. The dominant technologies of the latter half of this century will inevitably be zero-carbon technologies. Early deployment means seizing the initiative in development. Yet challenges remain formidable. Coal-fired power capacity continues to grow slowly, despite declining utilization rates. Low-carbon transformation in heavy industry requires more time. Carbon border issues in international trade are increasingly prominent. Yet the trajectory has shifted. As the world's largest emitter begins to decline, the most optimistic scenario under the Paris Agreement appears within reach for the first time. At Colossal Biotech's laboratory in Auckland, New Zealand, scientists are undertaking unprecedented work, bringing the moa, extinct for 6 centuries, back to life on Earth. This giant bird, standing up to 3.6 meters tall, once reigned supreme in New Zealand's forests, until Maori settlers hunted it to extinction. Project lead scientist Anya Lee explains, "We are not playing God. We are repairing the ecological damage caused by humans. Yet every participant understands. They are crossing biological and ethical boundaries. The technical pathway is intricate and complex. First, extracting severely degraded DNA fragments from museum-preserved moa specimens, piecing together a genomic sketch via novel sequencing techniques, then selecting the closest living relative, the South American tinamou, precision editing its genome, replacing each variant site individually. The most critical breakthrough comes from germline technology. We implant the edited primordial germ cells into the gonads of a surrogate host, allowing these cells to mature naturally within a living environment. The resulting offspring would carry partially reconstructed moa characteristics. But technology is the least of the concerns. Ecologist Mark Stevens questions whether the moa's original habitat remains recognizable. Introducing such a large herbivore could trigger unpredictable chain reactions. Do we truly have the right to alter an ecosystem twice? Maori tribal elders remain divided. Some support the project, viewing it as a symbol of cultural revival. Others strongly oppose, deeming it a second desecration of nature's order. Colossal's founder responded, "Our gene-saving technology has already proven effective in protecting critically endangered kakapo parrots. The extinction is merely a technical demonstration. Its true value lies in establishing biodiversity insurance vaults." Meanwhile, deep within Svalbard, the global seed vault has added 1,300 new samples of endangered plants. Tissue culture technology allows tropical rainforest species to await rebirth in liquid nitrogen. The coral larvae bank stores genetic material from 200 coral species, ready for reintroduction when ocean temperatures become suitable. Cambridge bioethicist Sarah Chun concludes, "Extinction reversal sparks such intense debate because it forces us to confront a fundamental question. What is the purpose of protecting nature? Is it to preserve a static snapshot of a particular moment, or to restore vibrant ecological processes? The answer will define humanity's new covenant with nature." In the neurology clinic of London's Royal Hospital, 53-year-old Marcus glimpsed hope for the first time. He had carried the Huntington's disease mutation for 2 decades. Each annual checkup felt like awaiting a death sentence. But today, the chart presented by his doctor revealed a steeply descending curve that brought tears to his eyes. The disease progression had slowed by 75%. This gene therapy, known as AMT-230, employs an intrathecal injection delivery method. Through a lumbar puncture, the drug is directly injected into the cerebrospinal fluid, allowing therapeutic molecules to ascend along neural pathways and precisely target the brain regions under attack. The drug's core component is antisense oligonucleotides, scientifically engineered short DNA fragments that function like precision-guided missiles to seek out and bind to erroneous messenger RNA produced by the mutated gene. This blocks the translation of these faulty instructions into toxic proteins, cutting off the disease's biochemical pathway at its source. Clinical trial data reveals that treated patients not only experience improved motor function, but also experienced a significant slowdown in cognitive decline. Most encouragingly, mutant protein levels in the cerebrospinal fluid of treated patients decreased by over 80% after 6 months. Project leader Professor Helen Carter cautiously emphasized, "This is not a cure, but a successful containment battle. We have transformed a rapidly progressing fatal disease into a manageable chronic condition." For the Huntington family, this signifies a generational shift in destiny. Marcus's daughter Sophia, now 18, had always refused genetic testing. For the first time, she seriously considers undergoing the test, knowing a positive result is no longer an incurable curse, but an opportunity for early intervention. In a ward at Boston Children's Hospital, 12-year-old Sarah is experiencing a medical miracle. Diagnosed with type 1 diabetes 6 years ago, she required 4 daily insulin injections and constant blood glucose monitoring as her daily routine. But today marks her 365th day post-treatment, without any need for exogenous insulin. Cell therapy employs a novel approach, harvesting skin fibroblasts from the patient, reprogramming them into pluripotent stem cells, then inducing their differentiation into pancreatic beta cells. These newly generated beta cells are encapsulated within a protective device made of alginate material and implanted into the abdominal cavity via minimally invasive surgery. The protective device's design is ingenious. Its pores allow glucose and insulin to pass freely, while blocking attacks from immune cells, like constructing an intelligent fortress for the fragile beta cells. It allows them to safely perform their insulin-secreting function. Among the 12 patients in the Phase 2 clinical trial, 10 achieved insulin independence like Sarah, while the remaining 2 still required supplemental insulin, but with a reduction exceeding 70%. All patients demonstrated significantly improved blood glucose control, with glycated hemoglobin levels returning to the normal range. Sarah's mother tearfully described the most profound change. She can finally join school camping trips like other children, no longer needing midnight blood sugar checks or worrying about hypoglycemia during vigorous exercise. Such freedom, once an unattainable dream for diabetics, has become a reality. The research team is preparing for larger-scale trials, aiming to secure regulatory approval within 3 years, to establish this therapy as the standard treatment for type 1 diabetes, radically transforming the quality of life for millions of patients. While humanity achieves localized progress, Earth systems approach dangerous tipping points. Monitoring data reveals the Atlantic meridional overturning circulation. This ocean conveyor belt driving global climate weakens at a rate of 15% per decade. Latest model simulations indicate, once weakening exceeds 34%, the system may undergo irreversible collapse, with catastrophic consequences. European winter temperatures could drop 5 to 10 degrees Celsius. Amazon rainfall could plummet by 50%. Monsoon disruptions would threaten livelihoods for 2 billion people. Accelerated melting of the Greenland ice sheet is even more alarming. Summer ice loss in 2025 reached the highest level on record. Satellite gravity measurements reveal the ice sheet has crossed a tipping point. Even if all emissions ceased immediately, sea levels would still rise by at least 1.2 meters. In Siberia's permafrost regions, methane monitors recorded abnormal spikes as thawed organic matter released this potent greenhouse gas. Under anaerobic conditions, latest estimates indicate twice as much carbon is stored in permafrost as in the atmosphere. A large-scale release would completely offset human emission reductions. Antarctica faces equally dire prospects. Iceberg A23A, nearly the size of the UK, is drifting toward warmer waters at 5 kilometers per day. This breakup is not an isolated event, but a sign of systemic instability in the ice shelf system. The collapse of the West Antarctic ice sheet may now be unstoppable. A special report by the Climate Scientists Alliance indicates that of 9 known tipping points, 5 are already activated, including mass coral bleaching, rapid Arctic sea ice decline, and changes in global atmospheric jet stream patterns. Yet the report offers a glimmer of hope. The remaining 4 tipping points, including large-scale Arctic permafrost thaw, can still be avoided through rapid emissions reductions. Every 0.1 degrees Celsius of warming matters critically. On the day the report was released, the UN Secretary-General stated, "We are racing against time, but we still hold the steering wheel. Every year ahead will determine whether we slide toward irreversible catastrophe or stabilize the climate system's critical equilibrium." The most alarming findings come from paleoclimate research. Reanalysis of ice core data reveals Earth's climate underwent dramatic shifts exceeding 10 degrees Celsius within a single human generation. Systemic inertia affords us a buffer period, but also means that once thresholds are breached, changes will unfold like an unstoppable avalanche. In this Anthropocene geological epoch, we are both the source of the problem and must become the creators of the solution. China's emissions reductions demonstrate action's effectiveness. Anti-extinction technologies demonstrate innovative potential. Yet facing the looming tipping point, What is needed is not merely technological progress, but a profound transformation at the level of civilization. The coming decade will reveal whether humanity successfully steers this ecological arc, or loses its final chance for redemption. Amid the chain reaction of tipping points, the answer lies in each person's actions today. Layla sat in the meticulously arranged treatment room, holding a precisely measured dose of LSD. This was her final hope. After 10 failed attempts with traditional antidepressants, guided by her therapist, she embarked on this profound psychological journey. 6 hours later, as the effects gradually faded, Layla described a profound experience. I felt reconnected to my emotions. Those suppressed traumatic memories finally found a pathway to release. This is not an isolated case. In strictly controlled clinical trials, 76% of patients with treatment-resistant depression experienced over a 50% improvement on the Hamilton Depression Rating Scale after a single psychedelic-assisted session. The effects lasted at least 6 months. The mechanism of action is gradually being unraveled. Psychedelics temporarily increase neural plasticity in the brain, making rigid thought patterns more flexible, and creating a valuable window for psychotherapy. Under the drug's influence, patients more readily access emotional material deeply buried by defense mechanisms. The treatment protocol is extremely rigorous, including thorough preparatory sessions, accompaniment by licensed therapists throughout, and a series of integration sessions to ensure the experience is properly processed. Even more encouraging is research on anxiety disorders. Social anxiety disorder patients undergoing treatment not only experience significant symptom relief, but functional MRI scans reveal reduced activity in their fear circuits and improved connectivity in the default mode network. A participating psychologist noted, "We are not substituting medication for therapy, but creating conditions that enhance treatment effectiveness." This paradigm shift may transform practices across the entire mental health field. David's car accident resulted in a comminuted fracture of the 6th thoracic vertebra. Based on imaging assessments, the neurosurgeon determined his probability of regaining walking ability was less than 10%. However, the newly implemented AI prognostic system yielded a different prediction: a 67% probability of restoring independent walking capacity. This AI system analyzed David's blood sample and examined a combination of 12 biomarkers, including specific inflammatory factors, nerve growth factor levels, and immune cell subset ratios. The integrated pattern of these indicators suggested his nervous system possessed strong repair potential. The medical team adjusted the treatment plan and adopted a more aggressive rehabilitation strategy. The results validated the AI's prediction. By the 9th month post-injury, David was able to walk with a walker. Similar AI tools are demonstrating value across various fields. In ophthalmology, by analyzing retinal scan images, they predict the 10-year risk of blindness in diabetic patients with 89% accuracy. In oncology, based on circulating tumor DNA testing, predicts lung cancer recurrence risk 11 months earlier than traditional imaging. In cardiology, combining electrocardiograms and blood biomarkers predicts complication risks in myocardial infarction patients, enabling more precise preventive interventions. These AI systems do not replace physician diagnoses, but provide insights beyond human perception. By processing the subtle interactions of hundreds of variables to uncover hidden predictive patterns, the most revolutionary application lies in preventive medicine. By analyzing health data spanning hundreds of thousands of person years, AI can identify early signals of disease progression, issuing warnings years before symptoms emerge, enabling medicine to truly shift from treatment to prevention. As more data accumulates and algorithms optimize, this predictive capability will continually refine. Future healthcare may resemble weather forecasting, anticipating health risks in advance, granting us the opportunity to take appropriate protective measures before the storm arrives. These 4 breakthroughs represent distinct frontiers in medicine. Gene editing conquers genetic disorders. Cell therapies replace damaged tissues. Psychedelics rewrite psychological trajectories. AI predictions seize health opportunities early. Together, they paint a future landscape where disease no longer signifies despair, and the boundaries of medicine expand at unimaginable speed. September 17, 2025, astronomers quietly crossed a historic threshold. Confirmed exoplanets surpassed 6,000. What was once an astonishing figure has now become routine scientific discovery. The 6,000th planet itself holds no special distinction. It is a scorching Jupiter-like world, orbiting a sun-like star 800 light-years away, with surface temperatures exceeding 1,500 degrees Celsius, and an atmosphere being steadily stripped away by stellar radiation. Yet its symbolic significance far outweighs its scientific value, marking the transition of exoplanetary research from an era of discovery into a new epoch of statistical analysis and characterization. From the discovery of the first exoplanet in 1995 to the current pace of discovering new worlds daily, we are finally beginning to grasp the true diversity of planetary systems. Chile's Vela Rubin Observatory has made a pivotal contribution to this endeavor. This giant eye, equipped with a 3.2 billion pixel camera, scans the entire visible sky each night. Using microlensing technology, it captures those cold, distant worlds that elude detection by transit and radial velocity methods. Rubin's chief scientist, Maria Chun, explains, "We are shifting from searching for individual planets to studying entire planetary populations, much like progressing from recognizing isolated strangers to understanding the diversity of an entire human society." Data analysis reveals surprising patterns. Earth-like planets in the Milky Way may be more common than expected. Habitable zone planets around red dwarfs exceed model predictions. Planetary system architectures are more diverse than our solar system. These discoveries are reshaping our understanding of planetary formation. Even more exciting is the next step. The James Webb Space Telescope has begun, conducting detailed spectral analyses of hundreds of exoplanet atmospheres, searching for signs of water vapor, methane, and even potential biosignatures. At a distance of 13.4 billion light-years from Earth, the Webb telescope uncovered a startling fact. Oxygen already existed in the galaxy Jade's GS Z14-0. The light emitted by this galaxy originated just 400 million years after the Big Bang. At that time, the universe was still in the late Dark Ages, with the first generation of stars just beginning to illuminate the cosmos. Yet the presence of oxygen indicates that at least one generation of stars had already completed their life cycles, scattering heavy elements throughout the universe via supernova explosions. Nobel laureate John Mather, who led the observation project, noted, "This discovery fundamentally reshapes our timeline. The processes of star formation and evolution must have occurred far more rapidly than current models predict." The abundance of oxygen is equally surprising. Though significantly lower than modern cosmic levels, it sufficiently demonstrates that chemical enrichment in the early universe was more efficient than previously imagined. These observational data are compelling cosmologists to re-examine the nature and evolutionary pace of the first generation of stars. The deeper implication is that the fundamental elements required for life formation were already in place during the earliest epoch of cosmic history. The oxygen atoms on Earth may have undergone multiple such stellar cycles before finally becoming part of the air we breathe. The combined observations from the Hubble and Webb telescopes have captured Neptune's auroral phenomena for the first time. This ice giant's magnetic field is exceptionally unique. Not only is it tilted relative to the planet's rotational axis, it also possesses multiple magnetic poles, resulting in complex and beautiful auroral patterns. Unlike Earth's green curtains, Nautilus auroras glow in the ultraviolet and infrared bands, generated by high-energy particles from the solar wind, interacting with hydrogen and helium in the planetary atmosphere. Fluctuations in their brightness reveal the impact of solar activity cycles. On distant planets, magnetic field measurements provide crucial clues, helping scientists understand Neptune's internal fluid dynamics. This ice giant may harbor oceans of supercritical water, enveloping a solid rocky core. The peculiar magnetic field configuration likely stems from convection patterns at different depths within its interior. Meanwhile, China announced an ambitious Mars sample return mission, aiming to bring back 500 grams of Martian rock and soil to Earth by 2030. 500 grams of Martian rock and soil back to Earth by 2030. This mission, named Tianwen-3, will employ an innovative orbital rendezvous approach. Unlike NASA's Perseverance rover's incremental strategy, China's approach is more direct and efficient. The lander-rover combination will collect samples on the Martian surface. Then the Ascent module will directly transfer them into Mars orbit, to dock with the waiting return module, before embarking on the journey back to Earth. However, the plan has drawn international attention regarding biosafety protocols. China has yet to explicitly state whether it will process samples in specialized sealed facilities, as required by the Planetary Protection Convention, or permit international scientific community participation in research. An unnamed European Space Agency scientist stated that Martian samples hold unparalleled scientific value, but any sample return mission must adhere to the highest safety standards. We must not repeat the mistakes of the Viking missions. Back then, we may have discovered Martian life, but missed it due to limitations in experimental design. The space sector is undergoing profound transformation. Commercial companies are taking on missions once dominated by nations. SpaceX's Starship successfully delivered 150 tons of payload into orbit. Blue Origin unveiled its lunar habitat design. Rocket Lab's Electron rocket achieved its 50th launch. This commercialization has drastically reduced costs. Low-orbit launch costs have plummeted from tens of thousands of dollars per kilogram to under $1,000. This enables more nations and enterprises to enter the space domain. Yet behind this boom lie new challenges. Near-Earth orbit is growing increasingly congested. Space debris has surpassed the 1 million mark. A single accidental collision could trigger a chain reaction, rendering critical orbits unusable. Geopolitical competition is extending into space. Multiple nations have demonstrated anti-satellite capabilities, while the Outer Space Treaty prohibits deploying weapons of mass destruction in orbit. Restrictions on conventional weapons remain in a gray area. The most pressing issues may involve resource allocation, rights to mine polar ice on the Moon, slot allocation in geostationary orbit, ownership of asteroid minerals. All require establishing new international rules. NASA's Artemis program continues to advance, but budget pressures have forced cuts to scientific missions. While the Europa Clipper mission was approved, exploration plans for more distant ice giants have been indefinitely postponed. Against this backdrop, the value of the Vera Rubin Observatory becomes even more evident. It not only searches for exoplanets, but also continuously monitors near-Earth objects, providing early warning for planetary defense. In this new era full of opportunities and challenges, the quest to explore the cosmos both unites us and reflects Earth's divisions. As one veteran astronaut remarked, our greatest gain from space exploration may be learning to gaze back at Earth from space, realizing the preciousness of this fragile blue dot. In the endless darkness of the universe, it remains our only known home. Deep within European forests, scientists have uncovered an unfolding biological marvel. An invasive ant species named Lasius neglectus is performing an unprecedented feat in nature. Its queen is cloning worker ants of a completely different species, Lasius paralenus. This discovery fundamentally challenges our understanding of reproduction and species boundaries. Imagine if a human mother gave birth to a child whose genes belonged entirely to another human race. That is what these ants are doing. Dr. Anna Schmidt, the lead researcher, described it. When we first confirmed this phenomenon through genetic analysis, we thought the samples must be wrong. We repeated the experiments over a dozen times, and the results remained consistent. This completely defies the fundamental rules of biology. These ants live in supercolonies, where ant nests stretch for kilometers without clear boundaries. Workers from different nests regard each other as family. This social structure alone is exceptionally rare, but interspecies cloning elevates it to another dimension. The mechanism remains mysterious. The most plausible hypothesis is that queens steal gametes from other species through some form of genetic parasitism, integrating foreign genes into their own reproductive systems. The resulting worker ants exhibit completely normal behavior, foraging, caring for larvae, defending the nest, yet genetically belong to another species. Evolutionary biologist Mark Chun notes, natural selection cares not for rules, only for what works. If this strategy enhances reproductive success, it will spread. Despite breaking every biological law we thought we knew, the implications of this discovery are profound. If ants can achieve this, how many other organisms are blurring species boundaries in ways we don't yet understand? The fundamental assumptions in our biology textbooks may require a complete rewrite. Through genomic analysis, scientists uncovered a startling fact. Different species of psychedelic mushrooms independently evolved the complete ability to produce psilocybin, using entirely different biochemical pathways. Imagine two teams of engineers who have never communicated, yet independently invent completely different methods to create the exact same complex product. This is precisely what occurred in mushroom evolution. Lead researcher Professor Zhang Wei explained, by comparing the genes of various psychedelic mushrooms, we discovered that the enzymes required to produce psilocybin share no common ancestral origin. They represent identical solutions, discovered by natural selection along two independent pathways. Such molecular-level convergent evolution is exceptionally rare. Complex molecules require precise enzymes to catalyze each synthetic step. The independent evolution of complete biosynthetic pathways in two distinct lineages implies psilocybin conferred a powerful evolutionary advantage. What this advantage is remains a mystery. Mushrooms produce psilocybin in their fruiting bodies, the part most accessible to animals. Perhaps it deters herbivores by inducing bizarre experiences in those who consume it, so they learn to avoid the mushroom. or conversely, it might attract certain animals. To aid in spore dispersal, animals consuming it could form vivid memories, thereby remembering and spreading the mushroom's location. The profound effect on the human brain was entirely accidental. Ammonite evolved millions of years before humans existed, and it happens to interact with our mammalian serotonin receptors. This is a prime example of evolutionary serendipity. Dog brains are more complex than we imagined. Recent research shows dogs can mentally categorize toys based on function. They don't merely remember individual toy names, but comprehend conceptual categories like ball or rope toy in a meticulously designed experiment. Some dogs classified tennis balls, rubber balls, and plush balls, all as balls, despite their vastly different appearances. This demonstrates dogs' capacity for abstract conceptualization. Beyond rote memorization, Dr. Matsuda, who led the study, stated, "This proves dogs' cognitive abilities far exceed our expectations. They aren't merely responding to commands, but constructing mental models of the world." An even more surprising discovery comes from the human brain. Scientists detected bacterial molecules in healthy brain tissue, whose levels fluctuate with the sleep-wake cycle. This challenges decades of dogma that healthy brains are sterile environments. These bacterial molecules likely originate from gut microbes and reach the brain via the bloodstream, directly influencing brain function and circadian rhythms. This provides fresh evidence for the gut-brain axis concept. Your gut bacteria may be influencing your thoughts in real time. Within the hive, researchers uncovered another marvel of symbiosis. While collecting pollen, bees also gather bacteria from the Streptomyces genus. These bacteria colonize the hive, producing natural antibiotics that shield the colony from pathogens. Bees do not intentionally cultivate these bacteria, but they benefit from this relationship. This is yet another exquisite example of symbiosis in nature. The most unsettling discovery comes from the black mamba. The world's most dangerous snake possesses venom far more complex than previously thought. Traditional antivenoms neutralize only the first wave of neurotoxins, but the venom contains a second wave of distinct proteins, causing a different type of paralysis. This explains why antivenoms sometimes fail. Even when neutralizing known toxins, the second wave remains lethal. Researchers are now developing new antivenoms to counter this dual attack mechanism. Each discovery reminds us, life is more complex than we imagine, more interconnected, more adept at breaking the rules. Just when we think we've grasped nature's fundamental laws, it always has new surprises in store, from ants cloning other species, to mushrooms independently inventing psychedelic compounds twice, from dogs capable of abstract thought, to gut bacteria influencing our brains. Biology continues to challenge the boundaries of our understanding. With its boundless creativity, at Nokia Labs in Helsinki, engineers are testing a revolutionary new chip, capable of transmitting 100 gigabits per second. What does this number mean? It's 10,000 times faster than current 5G networks, enough to download an entire 4K movie in the blink of an eye. The breakthrough of 6G technology lies not only in speed, but in its ability to utilize full-spectrum communication. Traditional wireless communication resembles a single-lane highway, while 6G suddenly activates a three-dimensional transportation network, operating simultaneously across multiple bands from terahertz to visible light. At the core of this technology lies silicon photonics, which replaces electronic data transmission with light pulses. Photons not only travel faster, but also carry more information. Most crucially, These optical components can be directly integrated onto standard silicon chips, meaning mass production will drastically reduce costs. Laboratory director Marcus Lindberg demonstrates the prototype. We are witnessing the ultimate evolution of wireless communication. When bandwidth is no longer a constraint, true holographic communication will become possible. You could converse with distant loved ones as if sharing the same room. The far-reaching implications extend to the Internet of Things. Every device in cities will gain ultra-high-speed connectivity. Self-driving cars can share real-time perception data. Medical sensors can continuously transmit high-definition images. Industrial robots can perform precise remote collaborative operations. China has announced plans to deploy commercial 6G networks by 2030, positioning it as a strategic high ground in the digital era. The United States and Europe are urgently following suit. This race for future digital sovereignty has only just begun. In the orthopedic operating room at the University Hospital of Zurich, doctors are utilizing a revolutionary device, resembling a caulking gun, yet capable of directly printing biomaterials to replace bone. The ingenuity lies in its specialized bioink, a precise blend of calcium phosphate, collagen, and growth factors, which hardens within minutes of extrusion. It immediately provides structural support for fracture sites. Subsequently, the patient's own osteoblasts gradually migrate into the implant and transform this artificial scaffold into genuine bone. Lead surgeon Anna Weber explains its value. Traditional bone grafts require harvesting bone from other parts of the patient's body, causing secondary trauma and pain. Metal implants, meanwhile, are permanent foreign bodies that may trigger long-term complications. This method perfectly resolves these issues. In a recent complex procedure, they successfully repaired a patient's maxillofacial defect, using a printed bone scaffold to perfectly reconstruct the facial contour. A CT scan 6 months later revealed complete fusion of the new bone, with virtually no visible signs of the original injury. This technology is particularly suited for irregular fractures. Surgeons can build layer by layer like artists, precisely matching the patient's anatomy to fill bone defects of any size, bringing hope to previously challenging cases. The device is currently undergoing multi-center clinical trials. If results prove positive, it will become standard orthopedic equipment within 2 years, revolutionizing the traditional paradigm of fracture treatment. At the frontier of quantum computing, scientists solve a critical challenge. New cryogenic device reduces heat dissipation by a factor of 10,000. This breakthrough enables quantum systems in space. Traditional quantum computers require massive cooling systems. Generated heat must be dissipated into the environment. But in the vacuum of space, heat can only be radiated away with extremely low efficiency. The new device utilizes metamaterials and specialized geometry, achieving unprecedented thermal management efficiency. Project leader Dr. Elena Varnin notes, this paves the way for space-based quantum internet. We can deploy quantum satellite networks to achieve absolutely secure global communications while conducting unprecedented cosmic observations. Meanwhile, brain-computer interface technology has made remarkable strides. A system developed by the Stanford team can predict spinal cord injury recovery from routine blood tests by analyzing the combined patterns of 12 biomarkers. AI can determine neural regeneration potential months in advance. The significance of this technology lies in personalized medicine. Doctors can tailor rehabilitation plans based on predictive outcomes, avoiding resource waste from ineffective treatments, finding the optimal recovery path for each patient. Apple is also quietly revolutionizing. They are fundamentally redesigning the iPhone architecture. eliminating distinctions between CPU, GPU, and neural engines, instead creating a unified AI-optimized chip, elevating on-device artificial intelligence to unprecedented levels. Imagine a phone capable of real-time translation for any language, without requiring cloud connectivity, while maintaining zero latency and complete privacy protection. This architectural shift will embed AI into every application, redefining how we interact with our devices. In materials science, novel wetsuit materials are saving lives, not by blocking shark bites, but by dispersing impact forces through multi-layered smart materials, reducing trauma severity, transforming potentially fatal injuries into survivable wounds. This material combines cut-resistant fibers with energy-absorbing layers, maintaining the flexibility of traditional diving suits while delivering unprecedented levels of protection. Perhaps most astonishing is biochar conversion technology, transforming toxic biocoal tar produced during gasification into useful biochar. This porous material can be used for filtration, catalysis, or even buried underground as a carbon sink, achieving negative carbon emissions. These technological breakthroughs may seem scattered, yet they point toward the same future, a world of abundant energy, seamless communication, precise medicine, and environmental sustainability. What we are witnessing is not merely the advancement of individual technologies, but an upgrade of the very foundations of human civilization, from Earth to space, from within the body to beyond. The boundaries of technology are expanding across every dimension. And the most exciting part is that these seemingly futuristic technologies have largely emerged from laboratories and are already transforming our reality.